So today we had a great time talking about population models, and we spent quite a bit of time making sure we got that logistic model derived. And so we missed out a little bit on doing some more word problems. And who doesn't love a good word problem? So let's do a few more. So consider this problem. Suppose that the population of a country, measured in millions, follows p prime equals kp 200 minus p. So that's not 200 people, that's 200 million people, where k is a constant. Its population in 1960 was 100 million and was then growing at the rate of 1 million per year. So predict the country's population for the year 2020. And you're like, oh, 1 million people per year, there's 60 years, that should be 160 million, right? Well, hold on. It doesn't say it's growing 1 million every year. It just says in 1960 it added 1 million people. Who knows what's going to happen? Maybe in 1970 the rate's higher or the rate's lower. It's not so clear. And well, actually, there's a secret here. I'll tell you the secret at the end. So, all right. So let's go ahead and let's talk about what we would do. So, well, what can we say? We know a couple of things. We see some key words. Well, a couple of things, of course, jumps out. There's this differential equation given to us, which tells us it follows the logistic model. And there's this piece of information that it was growing at the rate of 1 million per year. Now, growing just means it was going up, but there's that word, rate. Now, when we see the word rate, we should be like, ooh, that feels like a kind of like a derivative-like word, because it is. Anytime we see things like rate or change, it means a derivative is involved. So we say, this is going to be easy to solve for our k. Okay, what's going on? Well, let's think of 1960. We'll think of that as t equals 0, and our population is 100. So, since we know the rate is 1 million per year, we can say, okay, so that means p prime is 1. So now, plug it in. So we get that 1 is equal to k times 100, which is p, times 200 minus 100. 200 minus p. Well, that's 200 minus 100 is another 100. So 100 times 100, that's 10,000. Well, 1 with 4 zeros after it. And so we say, that lets us solve for k. 1 over 10,000. All right, great. Well, now what? Well, now we say we'd have to solve this, except we've already solved it. We know how it works in general. So we can say we pull out the formula because we'll have it. So the generic formula is mp0 over p0 plus m minus p0 e to the minus kmt. Excuse my voice. Now, let's plug in what we know. Well, we know m is 200 because that's what's given there. We know k. We also are going to say that p0 was the 100 because we're thinking of time 0 as being our data point. We oftentimes reset. If we have a problem, we say, look, whatever is our first piece of information, that's our 0 time. And so we have everything that we need. So lots of multiplying. So we're going to take 200 times 100. Wow, this problem's going to have a lot of zeros in it. So that's 20,000 divided by 100 plus m minus b0, which is 200 minus 100. I'll go ahead and write that as 100 e to to the minus, and now, well, we have m is 200 and k is 10,000, so it's 200 over 10,000. Well, you can simplify that because you can say, hey, look, cancel a 0, 2 over 100 is the same as 1 over 50. So this becomes t over 50. All right, well, pull out 100 downstairs, divide into upstairs, and we get what? Well, we get that. This is 200 divided by 1 plus e to the minus t over 50. Now, the last thing is, what is 2020? Well, 1960 was time equals 0, so we say, aha, 2020, well, that corresponds to 60 years later, so think of that as time equals 60. And by the way, we really see that years is the right measurements because it talks about the rates, million per year. So years is the right time measurement here. And now we see, aha, our answer would be 200 over 1 plus e to the minus 60 over 50. And, okay, so that's 200 over 1 plus e to the minus 6/5. That's the answer. That's it. Now, what is that? Well, we can go grab a calculator and find out. So I'm going to do that. I'll grab a calculator and I'll come back in just a second. Well, we know the answer now. This would be, by calculator, 153.7. And then, of course, we'd say million. So that's it. There's our population. So if you want the exact, using the model, or the, decimal using a calculator. And so we say, we see, that 1960, we were going at 1 million people per year, so 60 years would have been 60 million. But that means that what? Well, our rate of growth slowed down. And, that happens with time. Now, I said I was going to make a comment here. Well, it turns out that if you are very careful, if you have your m, which in our case we know is 200, then what your population is going to do is it's going to do something like that. It's going to sort of come up slowly at first, gain speed, and then slow down again as it approaches sort of its maximum capacity. When is it going to grow the fastest? Well, it grows fastest when you have half of m. So it's going to grow a little bit slower below that, and it's going to grow slower below that, right? But that's the point. Now, why did I point to there? Well, 200 million is the most we could have. We're at 100 million, so we actually start out at max speed. So the fastest rate of change we could hope for in this model was happening in 1960. So our 1 million per year, we maxed out our speed. And so that says that after that point, we'll grow, but we'll grow at a slower speed. So that's good. That matches with what we see here. So yeah, we still were getting growth, but because our speed was slowing down, we didn't get another 60 million. We got a little bit less than 60 million. So that's good. It matches with what we expect. So now we'll look at this problem. A particular breed of rabbits has their population fitting the model p prime equals kp squared. Now, if you think back to where we came up with the logistic model said, hey, as our population scales up, our death rate speeds up. In other words, bigger population, we expect even more people to die than a smaller population. And that's how you got that. There was this extra p floating around. But then we said, the birth rate in the logistic model still scales the same way. Well, this model could be, not only does your death rate speed up, but your birth rate speeds up. And if they're both doing that, then you get something like this model. So this is just as your population gets bigger, everything starts happening more quickly. So you have more births, you have more deaths, and so we should expect some sort of rapid increase. Well, at least that's our intuition, right? So let's see what goes on. Okay, so it does say that k is greater than 0. I'm sure that'll come into play at some point. Given that initially there are 6 rabbits, and after 10 months there are 9 rabbits, find P of t and describe its behavior. And now I feel like I have to be an English person and say, whoops, that should be its behavior, not it is behavior. Well, okay, shh, don't tell those English people. All right, well, here we go. Now, this one, we haven't been given a formula, but that's because it's not so bad. This follows the formula of a separable differential equation. So, in other words, we can say, look, dp dt is equal to k p squared, or we could say dp over p squared is equal to k dt. And now we're like, great, we've separated, and we know after separation comes integration. Integrate. Well, okay, the left-hand side, you can think of this as p to the minus 2. So you would say, okay, if it's p to the minus 2, add 1 to the exponent, which would give you p to the minus 1. We'll rewrite that. Then you have to divide by that new exponent, so that's minus p to the minus 1. Over here, well, we would have k times t plus some value c. All right, well, we can do a few things. We can move the minus across and write this as 1 over p. So that equals minus kt, and then plus c. I know. Wait, what? Shouldn't this be minus c? Well, a minus is a constant, and of course, constants can absorb constants. They're very good at sponging, putting them all together. So that tells us that, lo and behold, our population behaves like 1 over, because we just need to flip both sides to get p, all right, as c minus kt. Now, what do we have? Well, we have some information. We have 2 pieces of information. Well, that's good because we have 2 things we don't know, c and k. So between them, we should be able to figure out what's going on. So we have some information here that says initially 6 rabbits. So we say, oh, at time t equals 0, p equals 6. And then after 10 months, 9 rabbits. Oh, okay. So at time equals 10, p equals 9. Okay, well, let's start with 0. 0 is a good friend. We like hanging out with 0 because 0 simplifies a lot of things. So when you plug this in, you'll see that you get 6 is equal to 1 over c minus k times 0, or you get that c equals 1 over 6, right? Because that goes away, you flip both sides. Okay, well, that leaves us with this point. 9 is equal to 1 over 6, and then subtract 10 times k. Well, all right, flip both sides. We get 1/9 is equal to 1/6 subtract 10k. And we can move things around. 10k equals 1 over 6 subtract 1 over 9. And, oh, I'm almost out of space here in the corner. Okay, so here our common denominator would be 18. So you'd have 3 over 18 subtract 2 over 18, which gives us 1 over 18. So that tells us that k equals 1 over 180. All right, there we go. So we have c, we have k. So we can write this down. We'll come over here and say, lo and behold, our great aha, our population is going to be equal to 1 over RC, 1 over 6, subtract K, which is 1 over 180, and times T. Now, if you don't like fractions within fractions, and who does? Madmen, I think. Well, okay, so let's multiply top and bottom by 180. So this would be 180 divided by, down here, you'd have 30 subtract T. So there we go. There's our population. All right. So great. We did it. We found it. We found P of T. Now, you might say, hey, what's the behavior? Well, it's going to go up, right? As T increases, we're going to go up and up and up. And by the way, you can check to see if you simplified right by just verifying that the initial conditions still work. When you plug in 0, you do get 6. And when you plug in 10, you do get 9. So that's good. So what's happening here? Well, all right, at time 0, and then there's time 10, we see that we're going to start here at, at time 0, we're at 6, and then we're up to 9. So we start here, and we go there. Now, what do you notice about this function? Well, it has an asymptote. Where? Well, when the denominator is 0. So that would be over here at 30. So there's this asymptote. And so what's going to happen is that it's going to go up, but then it's going to blow up. And you'll see, of course, once we hit the asymptote, past 30, we can't see anything. But just think about what this is implying. You see, like, if it's going to go up here, this means that you have too many rabbits. It's going to take all the resources, and then there's going to be a complete collapse. So when you have something going up, and just all of a sudden there's a big explosion, an asymptote, it's going to lead to a collapse. And so that says at 30, that's it for the rabbits. So, they had a good run, and but they're only 20 months away from being done. Well, I guess that warns you, don't go too quickly, right? Slow down. So, all right, well, there we go. That's that problem. All right, our next problem. And this one, there looks like there's quite a lot of stuff here. But don't worry too much. Don't stress. Just because you see a lot of text doesn't mean it's bad. It's just that wonderful candy coating shell, and inside is that delicious nougat. So let's go through it. A colony of robots start on a small asteroid and then continuously build out. Consequently, the population corresponds with volume, because you're starting very small, and so as you're building out, you're basically becoming a solid sphere. So that's why of robots. So the population, you say, that whatever the volume is, that tells us how much we have for robots. Okay, so that's that part. While rate of growth is proportional to surface area. Well, that makes sense, because if I'm a sphere, if I'm solid, the only way I can grow is out, right? So the surface area represents how much is available for me to grow. So that's what's going on there. It is also the case that the robots slow down construction over time. Well, yeah, they get tired. Everybody gets tired eventually. So the model that describes the population growth of this robotic colony is P prime equals 5 e to the minus t, p to the 2/3. Now, okay, our math brain kicks in and says, whoa, wait a second. The other stuff was just candy coating, but this stuff, there's something here. Where p is the current population in millions, and t is measured in centuries. given that initially there are 1 million robots, so we get P of 0 equals 1, and it says find P of t. Okay, so even if we don't understand everything, or even if we don't pay attention, if we just grab these three pieces, we know what to do. Then, of course, there's this last sentence, also determine the number of robots there will be as t goes to infinity. Okay, so once we find P of t, we'll see what happens as we go to infinity. In other words, this part right here is saying to do the following. It means find the limit as t goes to infinity of P of t, the long-term behavior. So a couple of things I'll mention. The 5 is the proportional to, so we see a constant. The e to the minus t says, oh, as t goes forward, we start to slow down. So it's causing it to get smaller with time. So that's why that e to the minus t is there. Now, p to the 2/3, what's that? Well, if you think about volume of a sphere, you think of it as like, oh, it's like something r cubed, right? 4/3 pi r cubed. So if you take the cubed root, you essentially have r. The surface area of a sphere is 4 pi r squared. And so the surface area is r squared. So if you say how do volume and surface area relate, well, it's essentially you take the cube root of volume and then you square it, you'll get r squared. And so that's why there's the p to the 2/3. Now, we don't need to know that to solve it, but that's sort of the justification for why it's there. And it's nice to know why are things there. Okay, so here, again, this is a case where, it's not a logistic model, it's not an exponential model, but that's okay. We solve it like we would any other differential equation. So we say, all right, p prime, which is dp dt, is equal to 5 e to the minus t, p to the 2/3 power. We rewrite this, and we do it by separation. So this is very separable. So dp divided by p to the 2/3, well, we really should have written that as p to the minus 2/3 dp is equal to, on this other side, 5 e to the minus t dt. Okay, good. And now we integrate. So, integrate. Might as well say we integrate that, but these are the same thing. Okay, so p to the minus 2/3. To integrate this, we would add 1 to minus 2/3, which would give us 1/3. And then we have to divide by 1/3. Divided by 1/3 is the same as timesing by 3. So this will get us 3 times p. Okay, that's not so bad. Oh, to the 1/3. Don't forget that 1/3. Ha 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 ha. There we go. That's not so bad. So 3p to the 1/3 is equal to, over here, well, we'll have 5 e to the minus t. Well, the integral of e to the minus t is e to the minus t, but we've got to compensate for that minus. So that's minus 5 e to the minus t. And of course, plus some constant c. All right. Well, let's see. Maybe we can solve for our constant because we have p of 0. So we plug in our p of 0. We have that p of 0 equals 1. So we have 3 times 1 to the 1/3 equals minus 5 e to the 0, and then plus c. Well, okay, that's 3 equals minus 5 plus c. So, okay, c equals 8, right? Because minus 5, you add 5 across. Okay, so we're almost there, almost there. Well, what do we get? We get the following. We could say that p to the 1/3, we can say is 1/3, and now we have the 8 minus 5e minus t. And now, get rid of the 1/3, we cube it. So, lo and behold, P is equal to 1/3 times 8 minus 5 e to the minus t cubed. So there we go. There's our P of t. All right, so that's great. That's great. So now we have our answer to our first question. Well, but we should just define P of t. But of course, there's also the also. Also, determine the number of robots there will be as t goes to infinity. Well, let's look at what's happening. So we see there's only one t. It shows up here in this exponent. So as t goes to infinity, we just have to say, what is it doing to this part right here? Well, e to the minus t is going to go to 0. So this part is going to go away. So our answer is it's going to do that, right? Because that's what happens. And so we'll get, as t goes to infinity, the population is going to approach 8/3 cubed. And that's that part. Now you might say, wait, that's not a whole number. Well, it's approaching it. It's not getting there. And besides which, this is really 8/3 cubed millions, So quite a lot. And it'll take time. But that's it, It looked like a big problem, but it's like, oh, wait, actually, we just need to grab these pieces and know what the last sentence means. And like, oh, this is nothing scary, because it shouldn't be. Math isn't meant to be scary. It's meant to be interesting and informative and educational and occasionally, hopefully more than just occasionally, a little fun. All right, see you next time.